Yeah, if you, no, little bit if you can
little
increase,
better.
or you can use this one headphone.
Can
Because now is okay, but during the lecture, basically, again.
okay. It's now oh, the microphone here is maximum. This is the mute button. Okay. Now better? How about now?
Yes.
It's not. It's the same. Oh,
Yeah, it's
Yeah.
same, but I think it's okay.
okay, okay. Maybe tomorrow I can use a microphone.
Sure, sure.
So yeah, we can start now. Yeah, Nipun, please start
Okay.
this one.
Yes, sir. A very hearty good morning to Professor Mahesh, sir, Professor Mukesh Kumar, and a very good evening to Professor Chow and dear participants. I, Nipun Sharma, student coordinator for this course, take the privilege of welcoming this virtual gathering to the GIAN course on Fundamental of Photovoltaics, which is being organized by the Department of Electrical Engineering, IIT Jodhpur, from 14 to 19 February 2022. This workshop is a pioneering event initiated by the GIAN, which aims to explore the avenues and the possibilities of conceptual and pedagogical enrichment through meaningful exchange of ideas and the methods over these next 6 days. We believe that it would be successful in looking at the remarkable registration of the participants for this course. Before we begin, I would like to request Dr. Mukesh Kumar, who is Associate Professor with the Department of Physics, IIT Ropar, and Course Coordinator, to kindly give us a brief introduction of our course instructor and the brief glimpse of this course. Please, sir, over to you now.
Uh, Thank you, Nipun, and very good morning and good evening, Professor Chow. So, welcome to this GIAN course on Fundamental of Photovoltaics. And let me welcome Professor Chow with a very brief introduction. So, Professor Chow is an NSF IUCSR CEPS Center Site Director and a tenured full professor at Syracuse University, USA. Prior to joining Syracuse University, Professor Chow was Harold C. Hobbs Professor and Graduate Director at South Dakota State University. He was the director for 3,300 square feet class 1,000 clean room facilities at South Dakota State University. He has published over more than 200 peer-reviewed journals, articles in high-impact journals like Science, Nature Communication, Energy and Environment Science, Journal of American and Chemical Society, Advanced Material, Advanced Energy Materials, Advanced Function Materials, Nanoscale, and Nano Energy. And he has received 2015 Distinguished Researcher Award and 2014 AFO Butler Award for Excellence in Research, 2010 US NSF Career Award, and 2019 Bergman Memorial Award from US Israel by National Science Foundation. Professor Chow chaired many national and international conferences and served as a primary organizer for ACS Symposium, Organic Perovskite and Hybrid Solar Cell. So with this brief introduction, I welcome Professor Chow.
You, Dr. Kumar. And also thank you, the students and Hash and where can I see the students here? Be here, right?
Yes, they are in the
Oh,
attendees
I cannot
list.
see the students, right? I
They are
cannot
in
see
the
them.
attendees list,
You
Oh,
can
okay, I
see
see.
this.
right hand
Okay,
side.
I can see the list. Okay,
Yeah, you can see their name as well.
okay, great.
So
That's
whenever
okay.
this
So,
student they have the doubt, we will unmute them and they can ask directly the questions.
okay, sure.
Yes.
So can you guys see the slides here? I have the
Yeah,
slides. Can you see?
yes.
Okay. So since I came to the meeting late and then I I think, shall we start the course right now? Oh,
Yeah, please
Yes,
go
yes,
ahead.
we can.
okay. So good morning, everybody. So first, I think thank you both Dr. Mahesh. You guys helped me to organize these courses, and it is my privilege to talk about the courses. I actually have taught these courses for many years in United States. I have, simplified this, reduce the scope, and then modify this to fit to the GIAN course. Okay, so this is about the photovoltaic. We try to cover very basic concept, basic materials, device designs, and also tools used in this photovoltaic, and how these different materials can be used for different generations of photovoltaic devices. So the first class, I use chapter 1. That can also, you can just change the chapter to lectures. And then this morning, I think I sent Dr. Mahesh Kumar all my lecture slides. So that can be shared by with the students. So you guys should have access to my slides. Okay. So about introduction, basically I want to discuss why energy, especially the solar energies, are so important for our society. As you see, the human needs energy for civilization's growth and also enhance their living standard, right? So there's a direct correlation between higher, living standard and higher energy consumption. And then by average, you can see that each of us will use about 2,000 to 3,000 kilowatt hours annually. Okay, that's by average, right? No matter we are from, developing countries or from developed countries. By average, this is how much we use, right? So if you do the calculation for this, right, kilowatt hours, right? That watt hours, if you change the hours from to second, right? You can convert that to joule. So I actually typically when I teach the class, I've like students do the calculation, show me in the class. But since here, it's online, I'm going to just show, how you can, figure out, how much energy you need, right, for the entire world. You think about that 1 kilowatt hours, that's about 1 kilo is 1,000, right? Then watt hours, watt times, change that hour to 1 hour equal to 60 minutes, and then each minute is equal to 60 seconds. That's 36 seconds, right? 3,600 seconds. 3,600 seconds, and then times watt, that would be joule, right? That's 1 kilowatt hour, that's about 3.6 million joule, right? And then how many people we have on the world? We have about 7.2 billion, right? 7.2 billion multiply, 2,000 kilowatt hours, and that's basically what? 2,000 times that's 3.6 times 10 power 6, right? And then what they can get finally, for our human right now, if we consider 7.2 billion, then we need about 5.68 times 10 power 19 joule per year, okay? This is what the entire world will need, You can see this energy either from electricity or from other energy sources. That's all add together. And then let's look at the sunlight, right? We know that, the sun shines on the earth all the time, each day, either you're on the west side, on the east side, if you are west side like now in India, right? You guys in daytime, but United States, we are in west side, so we are at nighttime, okay? And then the earth will have half our surface is covered, is illuminated by the sun, okay? And then the sun showers the earth about 1.4 times 10 power 17 watt, okay? That watt is joule per second, as we just mentioned, right? And then now let's see, if in order to meet the energy, we just calculate 5.68 times 10 power 19. How many hours of sunlight do we need, if we assume we can utilize the sunlight 100%, and then, how many hours we need? Basically, we use the total joules, right, divided by this power. Then we get about 6.6 6.7 minutes, right? So if we can use this all the sunlight 100%, we do not even need 10 minutes. We just need about 7 minutes. Then that can meet the entire energy need for our Earth, for all our population. So how important for that? See, we get the free sunlight all the time. That's why if we can better utilize the sunlight, we can solve our problems, right? For our Earth, for our society. Then since sunlight, it's kind of free, it's renewable energy. We're not worried about we'll run out of sunlight, and then we're also not worried about that there will be a lot of carbon dioxide or other kind of greenhouse gas emission, right? So nowadays everybody is talking about what this is the carbon emissions, right? The world and all the countries, have agreement by 2050 we need to reach zero carbon emission, right, for the entire world, especially for these countries who emit a lot of carbon there, right? So that's just provide a background that we have a lot of sunlight. Then if we can find a better way to utilize the sunlight, we can solve our problem for our society. Okay. So here can shows, for different countries, this data probably a little bit old, but still can see that this human development index score, if that's 0.8 or above, basically means, the country use a lot of energies, right? You look at the countries that use a lot of energies, right? All these countries, right? Most of them are developed countries. They have developed, right? They use a lot of energy there. And then if you look at the bottom of this, this like more like Africa, right? Then these are developing countries, right? So you can see clearly to meet the higher living standard, people will use a lot of more energies. So the best line is that we do need a lot of energy, and then we do consume a lot of energy, right? So, and then we need this more energy to meet our what living standard. Especially, we hope every country will be developed countries, right? That's especially important. And then you can see that if we don't use energy wisely, we can cause problems, right? You see here, this, if you use a lot of this coal, right? If you don't have better way to just simply combust the coal, burn the coal, you get a lot of air pollution. And also, whenever there's, emergencies, it's like, it's about more than 10 years ago, right? That's the hurricane came, you see, then how people are in rush, how people in urgent condition need to gasoline, right? And also, we can better use the solar, right? You think about before, right? People use the solar, to heat up their food. And then also right now, I think in Asian, people, a lot of, put the water, the more like solar water, right, on the roof, and then the water will be heated. That use that shower at night, right? So, and then look about the different type of energy, right? Then there's some energy that is easy to transport but difficult to store. Other energies, right, that may be easy to store but difficult to be transport, right? And also there's some energy that's easy to store but difficult to transport, or difficult to store, difficult to transport. So if you think about the first one is easy to transport or difficult to store, that basically is what? Electricity, right? Also the sunlight, right? We think about the electrical powers, right? And then also the electromagnetic energy, right? All these has very high speed of transport, right? Think about the sunlight, right? Transport about what? 30 minutes, right? 30 minutes meters per second, right? And then that's the light speed, right? And then electricity, right? All the power line, electricity power, transport almost the same speed. Okay, so you can see that, but it's very difficult to store the electricity, or very difficult to store sunlight, right? So that's a problem. So that's why nowadays, I mean, a lot of resources or research goes to energy storage, especially for lithium-ion batteries, sodium-ion batteries, sulfide batteries, or different batteries. So a lot of type of energy is, very interesting. That's right now we use a lot, right? When you drive cars, if you don't drive EV cars, you use gasoline, right? Then, or for trucks, they use what? They use diesel, right? Then these are easy to store but difficult to transport. And then the other energy is solar energy, right? Solar energy is very important, especially for people live in the northern part of the United States, Canada, right? Then people use a lot of solar energy for winter because it's pretty cold, right? You have to add this heat energy into the house, right? So that's the solar energy is difficult to store, also difficult to transport. Okay? So electricity, right? If you look at the electricity, right? Electricity is a popular form of energy, and then provide a lot of convenience for us, right? Think about, look at your house, right? You have all these appliances, you have all these electronic devices. All of these need to be charged by electricity. Okay, so that's why it's very important. So the electricity, is also important for industry, right? Industry or business building. So other type of energy there, such as coal, natural gas, or oil, and then if you look at these are basically formed, from remains of plants or other living species. They are millions of years, right? You can see when you look at these, plants or living species, their energy are all originated from the sunlight, right? Because they, take the sunlight and then they grow themselves. They get energy from the sunlight, right? And so that's the process for them. That's basically you store the energy for millions of years, the solar energy for millions of years, and then with high pressure, very deep underground gas for all. That's what people see, right? Since now the consumption speed is very higher, very faster than the energy, the chemical energy, formation during millions of years. That's why we think this is, people believe these are not sustainable. If you keep use this, one day you will use up all these fossil fuels energy, right? Because the process to form the fossil fuels is so slow compared to the way people consume them. Okay, so and then this photosynthesis, this also provide a lot of way for renewable energy or sustainable energy. If you're thinking about biofuels, biomass, this is also part of renewable energy. That's also originated from the sunlight. If you can continually grow the trees, the grass, and then you find a better way, put them to fossil fuels, to gasoline, to ethanol, and then you can make that sustainable way. Right? So overall, there's a problem here, right? If you use a lot of fossil fuels, you use a lot of coal, gasoline, diesels, you know that you will emit a lot of carbon dioxide and other kind of GHG, right? That's greenhouse gases, okay? So if you look about, what is the most industry that emit greenhouse gases, that's from transportation, right? Look at all these passenger cars, all the trucks, and then all of that, right? They use a lot of energy, and then they emit a lot of carbon. They emit about, I would say, 40 to 50% of the total carbon from all the carbon emission. So that's the big number, right? That's why, nowadays the electric vehicles become so hot, right? Because if we want to solve the problem for this global warming, and then we have to address the problem from the transportation sector. Okay. So, and then renewable energies, right? We talk about renewable energies, and then of course, since this course is about the photovoltaic, so photovoltaic is one of the major renewable energies, and also as we just calculate that the sunlight provides us a lot of energies. So that's actually, if we can better use them, we can solve our problem. So there are other renewable energies too. There's a wind energy, right? Whenever people talk about the solar, people also talk about the wind, right? Wind plus solar, right? Because these are very good complementary energy sources. sometimes you have wind, sometimes you don't have wind. But also sometimes you have a sunlight, sometimes you don't have sunlight. So if you can, combine this together, when you don't have sunlight, if you have wind, right, then that'll be good, right? If you don't have wind and then you have sunlight, that's also be good, right? If you have both, of course, that's better. If you don't have both, you don't have any of them, and then you can add energy storage. And then there's others like hydropowers, biofuels. All these are the major renewable energies there. And then if you think about that, as I just discussed earlier, all these originate from the sunlight. Okay, wind from the sunlight, right? Because the sunlight, heat up the oceans, right? And then you have a lot of vibrations of this water come from the oceans, and then that moisture in the air will flow, right, with the wind to the inlet, right? And then they accumulate, and then you get the raining, you get slows, all these kind of things. Then the solar energy, of course, either solar water, solar thermal, or solar electricity. Both of these are from the sunlight, and the hydro is the same thing, right? You have the raining, you have slows. That's why you have the rivers, and then you can build the dams, right? You can store the water there. The water flow can convert to electricity, right? And biofuel is also, right? Whenever you grow trees, grow grass, grow the corns, all these are from the sunlight, from the photosynthesis, right? This is a major energy sources. And another type probably is the geothermal, right? Geothermal is also renewable energy, but that's probably not from the sunlight. That was, formed when the Earth was born. When the Earth was born, and then the geothermal energy was here that time, but it's insulated inside in the Earth so that the energy is released slowly. Okay. Some other energies also is important, but people may worry about their, byproduct or their waste. For example, nuclear energy, right? Nuclear energy basically is from what? Splitting, that's also for fission, right? That's basically you have what? Nuclear split, right? Also you have merging of fusion, right? You think about the sun, right? The sun, you have hydrogen fusion happening. That's why, we emit the sunlight, and then the sunlight reaches to the bright as energy, right? That's because of this. That's also nuclear energy, but it's far away from us. It happens on the sun, right? Okay. There's a basic equation. I think you guys all know that, right? When the mass change, especially if it's splitting or fusion, because the mass of the atoms or mass of nuclear change, then that mass multiply this, square of the light speed. That's why the energy is huge, right? So nuclear energy, I think the problem probably typically the adoption by general public kind of scary, right? Because nuclear, it's worried about the radiation there. So there's natural disasters, right? And if that nuclear energy is not, well protected, then that can be a problem for the public, also big problem for the environment. And the other thing be the byproduct of nuclear reactors can be a major issues, especially from the radiative material, because it really take a long time for them to decay themselves. So I think nowadays probably people don't worry about that. Don't doubt the global warming, but when Trump was here, I think their administration kind of doubt the global warming, whether it's real or fake. Okay, so but there's some data shows that, right? If you look at the past, about 60 years to now, this data probably I need to update this data. You can see, oil production has been increasing, and then meanwhile you can see, atmosphere carbon dioxide has been increasing as well. They are well correlated, right? There's no problems. There's no, the evidence here is pretty clear that, right? Carbon dioxide and also other greenhouse gases, their concentration has been keep increasing, right? That is a very consistent, very well consistent with the oil production, energy we use. And then here comes the questions of the theory. Why, global warming? Why these greenhouse gases were added to the global? So basically, if you think about the Earth, right? The Earth in daytime, you have what? You have the sunlight shine on the Earth. Now, since you have the atmosphere, right? You have atmosphere, you have different gas molecules in the atmosphere. When the sunlight shines to the atmosphere, all the molecules in the air will what? Will take the energy from the sunlight, right? And then their vibration will get stronger. They either have faster vibrations, higher, intensity, amplitude of their vibrations. But during night, when the Earth turned itself during night, at night, the air temperature cool down, right? And then that air molecules that take the energy from what? From the sunlight will emit the extra energy out during night, right? So typically, if you have certain amount of the greenhouse gases, the atmosphere of the Earth itself will be under balance. How much absorbed during daytime, and then you release how much out, right? So in overall for a long time, this Earth under balance. How much comes, how much will release, right? But now since the human activity, right, we add too much these greenhouse gases into the atmosphere. We basically broke the balance, right? We add more of these gas molecules there, absorb more light, absorb more energy there, and then they cannot release that energy, right? At night. And then as time goes, that's why the energy in the atmosphere or the energy from the atmosphere, to the Earth will be keep increasing because you keep adding these greenhouse gases that, can store or can absorb more lead energy from sunlight. Okay, so that's probably especially the carbon dioxide, methane, and kind of nitrous oxide there, especially they absorb, infrared light very strong. If you look at the sunlight, only 50% of the sunlight, if you separate the sunlight frequency or sunlight spectrum in three parts, right? UV, visible, and then infrared. Then UV basically have only 7% of energy there. Okay, and then the other 93%, about half of energy from the visible light, half of energy from infrared. Okay, so infrared light is very easy to be absorbed by the gas molecules, especially you have carbon dioxide, you have methane and other nitrous oxide, and then they can easily absorb this infrared light, and then they will not be able to release that fast because they have too many of them here. So here shows a model. You can see, the sun, shine to the Earth, right? And then, of course, the first interface between the space and the atmosphere. At that moment, there's interface there. There's reflection. Then the sunlight, including when I talk about the sunlight, not only the visible light, including the UV light, also infrared light. Then goes through the atmosphere, be absorbed by the atmosphere, and then come to the surface of the Earth because there's refractive distance as air, and then the land surface or the ocean surface. There's reflections there. Their reflection back also, that sunlight energy will also be absorbed by the moisture molecules, gas molecules, air molecules, right? Then you see, how much comes, how much reflected, also this atmosphere store in daytime, and at light we emit them back. Okay, but once you add more absorbance, and then you break that balance. That's why this happens with. So with all this, you can see that we do need, alternative energies, right? So, and then the alternative energies, right, must be clean and sustainable. Then must have huge capacity for generations, few terawatts. That's basically, if you think about the power, right? The power generation side, that should be big, right? And because you cannot, unless you think about the solar, you can install the solar on all the buildings, and then that help. Otherwise, if you generate a lot of, if you have a few sites to generate a lot of energy to meet the society need, and then you do have, you need to increase this capacity of the generation. Then the major wise, as I mentioned earlier, right? You have photovoltaic, you have wind, you have biofuels, hydro, geothermal. Okay. And here shows, and people trying to use solar panels directly on the airplanes, also on these, cars. Since the sunlight, if you think about the sunlight energy density, not energy density means error, if you think about the energy per meter square, because 1 meter square you have only 1,000 watt, right? And then if you think about the solar cells efficiency, like 20%, 1 meter square you only generate what, 200 watt. 200 watt one day you think about 8 hours, but in the morning the sunlight pretty weak, evening sunlight pretty weak. The sunlight is the highest during noon. Then if you think about the noon time, that's 1,000 watt per meter square. Each day average out, you have only 4 hours at that moment. Right? That is about 4,000 watt. 4,000 watt, and then times what? Times 30%, and then you get times 0.2, get like 800 watt. Okay, 800 watt hour. That's why if you think about 1 meter square, you don't generate a lot of electricity. But since the surface of Earth is huge, it's very big, and then if we can use 100 miles times 100 miles, install these solar panels that generate about 3.34 terawatt. Okay, that only has like 13%. That's probably the common efficiency from polycrystalline silicon solar cells. This about the energy used by United States in 2005. Nowadays, this probably much bigger. Okay, but now the efficiency is higher. It's much higher. So, and also you can use more land. If you think of the land of Earth, some people may argue that because we use this land for farming, for agriculture, for other kind of things, for cities, right, for civilization. But we do have a lot of land that cannot be used for farming for human to live, right? Think about the desert, right? Desert has huge amount of areas, right? So here shows, for United States, this data, if Nevada, right, on the west side, there's a lot of desert. Think about the desert in Nevada, right? If you take 100 miles times 100 miles, in 1 mile is 1.6 kilometers. That's about 160 kilometers times 160 kilometers. It should generate sufficient energy, for entire nation. Okay. Then nowadays, probably I have some slides later to show that the PV industry has been growing very fast, right? So if you consider last century, probably the road or the highways has been built by United States. That's a big thing. Okay, in the future, next generation, probably, okay, also in last centuries, the grid, right? The power grid is another big project. But for this century, I think the big project will be renewable energies, right? That renewable energies, I think, photovoltaic and the wind and combine and others, right? Maybe the photovoltaic will be the big project that help the world to be sustainable, solve this global warming, rising problem. So with that, you can see the industry has been growing pretty fast, right? In 2006, it was about 10 billion. That's revenues. Then 2007, that's the 2007 about 13 billion. Then by 2 years ago, that was like 345. So this number has been keep increasing, maybe 20 to somewhere between 20 to 30% of annual growth next 20 years. Okay. Then the PV module shipment, this PV modules, this here is talk about like the 30% growth, 10 years period. And this has been increasing. And so a lot of industry, people they try to compare the PV industries with other industries. That's particularly circuit, IC, then all the IC and display. This year you probably heard about the supply chain, disruption, also the shortage of this, ICs that cause a lot of issues. But overall, all this industry has been mature. Growth has not been that fast as you see in the solar industry. The solar side just started, okay? Just started. So their growth will be really fast and also here shows, I think you guys probably heard about the Moore's law. That's basically if you can, double, if you can double the, basically, every 2 years, the chip capacity will increase by 2 times or double every 1.5 months. Okay, so then that's why you can see the size of the computer smaller and then their capacity meanwhile has been increasing. Right, that's Moore's law. Okay. I think that now can be used to describe probably the PV industry, right? Installation capacity and then cost. And more installation and then lower will be lower of the cost. That's why right now, if you compare the cost from the wind and from PV, they are comparable with the fossil fuel cell. Okay, so here shows that you see how fast this grows, like exponential now. The see 15, 20, 25, different models and predictions, and then the growth will be like this for many years ahead. Then another things that help the fast growth of PV industry, the cost, right? You think about like 40 or 50 years ago, the cost per watt is cost per watt, okay? About $40. This watt of peak watt. When you think about the photovoltaic, you want the photovoltaic, the solar panel to provide energy at the peak, right? At the maximum power point. Okay. That time, 1 watt costs about $40, right? 10, 20, 30, 40. Okay. Nowadays, think about this, since this data is, I think this data is used probably a few years ago. Now it goes about 50 cents or 60 cents or even lower now. And then many of these costs is not from the hardware. Most of the costs are from the soft costs. Soft costs basically cost about the installation cost, the labor cost, the maintenance cost, the shipment cost. All these costs at about 60% of solar panel. But overall, the cost has been dropping so heavily, so significantly. That's why everybody can afford solar on their. The only things that still stop people is that you have to, install that at the beginning, right? Like you buy a house and then you pay for the money at the beginning. So when you install that, seems cost a lot of money, but if you average that for 20 or 25 years, that costs almost nothing. You should be able to get the investment, in 5 years or so. Then after 5 years, if the maintenance is not significant, you basically get free energy each year. So here shows the commercial solar electric systems. Then it shows you can see the PV systems, how big it is that. Then what is the average you can get the power and also cost, and then the years depreciation. Then also savings. You can see each of these. Right? Small office to phone shops and then institute to buildings. The more install, the more you can save in, right? Saving here. The more you install, the more you can save in there. But you do need to have a big investment at the beginning to install the solar panels, to buy the panel, to install them to your house. Okay. So this provide opportunity still for research and development. Even the silicon solar cells has been become so cheap, but still, people always want to make it cheaper so that even the upfront fees to install the solar panel will be low. Okay, that's why The industry right now still relying a lot of silicon solar cells, but you can see that there are other type of solar cells, Dyson style solar cells, organic solar cells have been very hot in the last, a few years ago, maybe from the last 15 years to 3 or 4 years ago. Nowadays, a lot of research focused on the perovskite. That's another type of solar cells, also called next generation solar cells. Their efficiency have been, reached the same as the silicon solar cells. So, and also, if you build double junction, multi-junction, you can easily tune their band gap. So this provide a lot additional advantage for solar cells. Okay, so here you can see in the past, typically people probably were have 3 generations of solar cells. The first generation basically, single crystalline silicons. That's why C means single crystalline, or crystalline silicons. Single crystalline, monocrystalline means the same thing. Okay, that's basically the phase is one or single, single crystals. Okay, and then the polycrystalline is also the first generation. The second generation, because you guys probably all heard about the 2006. At that time there's shortage for silicon wafers. That's why people try to reduce the amount of materials using, especially amount of crystalline silicon. Then at that time, a lot of companies try to commercialize thin-film solar cells. Basically, you reduce the material thickness from silicon that's about 500 micrometer to 1 micrometer. Use that very big. Either 1 micrometer or tens of micrometer. You can reduce that 10 times or more than. Then you can see different technologies there, like amorphous silicon, microcrystalline silicon, CIGS, that's copper indium, gallium, selenide or sulfide, and telluride. These are still being made today. People are still. I know a company from they're still trying to the company. And then the third generation basically the organic base. You can think about the Dyson style solar cell, Polymer solar cell, Oligomer, or the perovskite solar cells. But nowadays, people don't talk a lot about Dyson style solar cell because it's liquid electrolyte there, or polymer electrolyte. The polymer solar cells has still been, a lot of research going on there, but not as significant as perovskite. Now perovskite has been the major, research areas. So with that, I think this about the introduction. This is lecture 1. Basically, give a big pictures about how the energy is being used today. Then what are the major type of renewable energies? And why the solar can stand out as a major part because of the sunlight. We get a lot of sunlight, and then their cost, and then what will be the future of this. So this is just introduction, and the next lectures we're going to talk about the basis of photovoltaic, and then we'll go about how a basic device look like, and then how you can calculate the solar cell efficiency, how you can characterize their open circuit voltage, short circuit current, fear factor, and also the equivalent circuit to understand the solar cell, how they can work, how you can do the modeling of the solar cells. Okay, so I'm not sure here. I start next lectures, or I may take any questions. Anyway, if you have questions, you can ask now. Can you guys hear me okay?
Yeah, thank
Yeah,
you, Professor Chow. Now, if any question, you can just type in the chat box, or you can raise your hand.
Yes, Professor Chow, thank you. It was a very nice introduction. So first, I would like to one question that the CO2 emission in production of a solar cell is ever able to meet the CO2 production by the normal processes like thermal or other power production sources.
Okay, so you talk about the CO2 emission when you fabricate the solar cells, right? Because you need to use the silicon wafers, right? Silicon wafer be produced from the what? silicon ingot, right? And then you
Yes,
get the
sir.
wafers, and then you have all the microelectronic fabrications, right? You have the p-type doping, n-type doping, right? And
Yeah.
then you form the junction, and then you form the metallization or the product. Okay, that's really a good question. Okay, so if you think about if nobody made this solar cell before, now you made the solar cells, and then the process will be not efficient. You do generate a lot of CO2, right, for the first generation solar cells. But nowadays, since the processing have been improved, if you especially think about the cost, and also, you know, nowadays you don't need to use the energy from fossil fuels, right, to fabricate the solar cells. Since there has been a lot of solar panels being installed, right, you can use the electricity from this solar cell generate electricity to produce new solar cells. And then you can see, your carbon emission still stays the same as you produce the first round of solar cells, right? So all the future solar cells can be made from the energy by the solar panels, right? And then there will be no carbon emission there, right?
Okay. But sir, right now, is there any fabrication which is fabricating these solar cells by using photovoltaic energy itself?
Oh, so nowadays, if you look at the percentage of energy generations, has been increasing. Uh, I don't know the word, I know in United States, in China, Japan, Germany, they have in United States, especially in California, their ratio, their percentage has been very high. The energy generated from the solar panel is so high, so that will be support or a lot of not only uh, for household and also for industry.
Okay, okay, sir. And
And
there is
then
another.
if you compare the carbon emission, right? Use the photovoltaics, right? Uh, with other energy sources, photovoltaic the carbon emission only 15%. No, their whole process compared to other kind of fossil fuels that can be 60% higher.
Sir, one more question that the after the complete life cycle of solar panel, there is problem of recycling. Actually, nowadays the whole world is facing the problem of e-waste disposal.
Okay, that's another very good question. Excellent question. Yeah. So nowadays, because solar panel has like 20, 25, 30 years lifetime. So nowadays people don't run too much, but the government has been pick up now. Now, if you look at the Department of Energy from United States, they start to make programs there, develop new ways for the recycling of the solar panels. So in the future, yeah, the recycling will be a big industry when the solar panels become so common. So that will be big industry, the same as like silicon, the same like battery recycling. Yeah. So that will be a big industry there. So I think a new technology will be needed to recycle this silicon solar cells, solar panels.
Okay, okay, thank you so much, Professor.
No problem. These are all great questions. Thank you.
Sir, we have one question from the participant, Adish. He's asking, what is the accurate efficiency of PV solar cells?
Okay. The efficiency of so if you think about the efficiency of solar, there are different type of solar cells. The highest efficiency from 3.5 is gallium arsenide, and then the dope anodide, with other element. Then they make four junction, triple junction, four junction or six junctions. You can achieve efficiency somewhere 49% or 50%. But this efficiencies, this kind of solar cells is very expensive. These are only used for satellite for space application. Okay, so if you think about for the silver silver use, like use on Earth, this basically will be silicon solar cells. The silicon solar cells lab report efficiency is highest efficiency about 25%, 24.6%. Not much improvement there. It's reached almost the maximum, if you think about all the losses. We will talk about the loss mechanisms for solar cells later. And then that's for silicon solar cells. And then the single crystalline silicon solar cell, about 25%. And then polycrystalline, I think probably, somewhere from 12 to 15% efficiency, the best efficiency. The amorphous silicon, about 8%. And then the other type of solar cells, as you see here, like next generation dye-sensitized, that's about 14%, 13%. Polymer solar cells, about 19%. Then the perovskite, about 25%. That's just when you look at the efficiency, the efficiency of different technologies are different. I hope that I answered the questions. Yeah.
So one of the participants wants to ask question. Himanshu,
Yes, sir. Hello.
please proceed.
Yes.
Yes. Thank you, Professor, for such a wonderful presentation. I want to ask one question, sir. As we know that we have such a great technology, solar technology, but we are still facing the intermittence problem, as well as we are constrained with the cell temperature. So, however, you described that perovskite is the third generation, but we are getting efficiency lower than the traditional silicon panels. So, what are the factors which are not allowing the efficiency to be higher for the solar cells, please, sir?
Okay. So yeah, this is a great question. You probably read about the perovskite solar cells. When I talk about the highest efficiency for perovskite, that's basically lab-based small area solar cells. But if you make solar panels, this perovskite will be lower, and also their lifetime will be shorter than silicon solar cells. So basically, if you compare the two materials, right, the silicon is a single crystalline silicon solar cells, or even polycrystalline silicon solar cells. They are much more stable than the perovskite. But perovskite is a polycrystalline, and then you think about silicon, it's just silicon, right? You have only one element there. But perovskite, you have what? You have if you think about, you use lead, you use Ma, and then you use many elements there. It's the structure is so complicated, and then it's polycrystalline, and then the atoms will diffuse around when you build your solar panels, and then you put your solar panel under sunlight, and then there's morphology evolution, right? There's ions diffusions, and then all these will cause problems for the perovskite. That's why its efficiency will be dropping, and perovskite also does not like moisture, or does not like oxygen. I think silicon does not like moisture or either, right? Because that's why silicon solar cells are being built in glasses, right? You have one glass on top, another glass on the bottom. Basically seal your solar cells inside the glasses. So I think that can be the same thing to be done for perovskite solar cells. If you build solar panels, you can get rid of moisture, you can get rid of oxygen easily, but the thermal stability can be a big problem, especially if the ions can be diffused easily, and then the quality will be changed under temperature change. That can be big. Yes.
Thank you, sir. Sir, as you told that perovskite uses organic technology, so what do you say that the future will be good if we use organic elements rather than using inorganic?
Yeah, there's one, I think, generally speaking, that's true. If you use all inorganic components, it will be better than the one you use organic components. Because organic components that basically will produce stability, right? Especially the thermodynamically unstable temperature change. If you have all inorganic, and then you probably can build a better crystal structure to hold these elements so that they cannot diffuse easily as they soft material, like carbon materials in the structures. That's true, yeah.
Thank you, sir.
And also people try to make these 2D structures. 2D structures, thickness will be thinner, and then the crystal structure may be better, stabilities. And you will not see this structure to. That's why a lot of people reported better, longer stability than 3D structures.
Thank you, sir. We have another question from Nilay Basu. He's asking about the prospects of oligomer solar cells. And further, he's asking, isn't it as similar to polymer solar cell?
Okay. What is his question about Onigama? Is that his question?
Yes, sir. Prospects of oligomer solar cells.
Oh, okay. Yeah, Onigama, if you think about the Enigma personally is also a type of organic type solar cells, just because of this molecular weight will be smaller than polymer, but maybe bigger than small molecules. Then that is Enigma solar cells, but they have almost the same problems as small molecule based solar cells or polymer solar cells, stability issues, and then the reproducibility for large scale manufacturers. I think maybe the major problems will be the stability. If you think about all the organic based solar cells, in the carbon based, right? Like carbon based, you think about and then this carbon based polymer, because they have single double bond, single double alternate structures, because you won't have these pi bonds, pi electrons, right, in these organic based materials, so that they are kind of have delocalization of electrons, and then they can become semiconductors. They have good, electronic or activity, right? But these double bonds, typically can be easily oxidized by oxygen or moisture, right? And then the double bonds will be broken. If you lose the double bonds, lose the pi bonds, and then you know that you will bring a lot of defect, and then you will not have a good semiconducting property, electronic properties. That can be the issue. That's why all these organic based, their major problems maybe not used on the for mass power generation for big buildings on large scale, but this more like for consumer electronics, right? You can build flexible solar cells, you put into your tent, put in your to backpack, and then you can use that to charge your cell phones. Maybe for military applications, because these are lightweight, can be easily built on their tent, right? Build them, and they don't need to carry very big, batteries, very heavy, silicon solar cells. That can be the benefit.
So we have one last question from Sumit. He's asking, can we use a reliable battery for the photovoltaic system?
Can you repeat the question? I didn't
So
get
he's
what kind
asking,
of
can
battery?
so he's asking, can we use a reliable battery system for the photovoltaics? I mean, I guess he's asking for the long life of the batteries, or if there any present as of now.
Oh, for the batteries?
Yes, sir.
For the long life battery as storage for solar cells?
Yes, sir. This is what I guess he's asking because he has question like, can we use a reliable battery for the photovoltaic system?
Oh yeah, okay. So typically, nowadays, if you think about the future of the solar panels or solar energy, right? Solar energy are not stable, not reliable, because sometimes you have, really sunny days, and then sometimes you have what? Raining days, cloud days. You also have daytime, nighttime, and then even during sunny days, you have pop clouds there, right? It's pop cloud moving all the time. So the sunlight shine on solar panels are not stable, right? So in order for you, for people, for your end users, you use the solar electricity. You don't want to see now I have solar electricity, later I don't have because you don't have sunlight, right? So that's why the energy storage can be a big thing for solar panels. Another thing would be, complementary energy generations, right? You can use the wind, you can use solar, you can use hydro to mix each other. If one is not available, the other one will be available. So, but to make sure 100% energy storage will be very important. Nowadays, energy storage, you can think about lithium-ion batteries, in the future, probably sodium-ion batteries, and also will be long-duration energy storage can be. Right now, United States has put a lot of money to the non-duration. You think about, your energy storage should provide electricity that can last for 8+ hours or 10+hours. That exactly when you don't have sunlight for 8 hours, you don't have wind for 8 hours, this energy storage should be very cheap, should be able to reliable for you to. But for right now, the technology is not there yet. We still need to work on developing the technology on duration. So nowadays, I think the common one probably hydro, right? You can just store the water there. When the water run down, you generate electricity from the water. That's a hydro can be a very, a perfect candidate for as long duration energy. Okay, so these are all great questions.
Yes, sir. I guess we are done with the question. May I request Professor Mukesh Kumar to kindly close this lecture?
Thank you very much. It's a really interactive session. Students asking many questions, and I believe all students will enjoy this like special kind of a GIAN course on photovoltaics. So there is a need of ours, as we know that renewable energy is no longer a choice. That is a necessity of the time now. So thank you very much, Professor Chow, for kick-start this event with this very nice presentation. Thank you very much, and see you all in the evening at 6:30 in IST, Indian Standard Time.
Great. Thank you, Dr. Kumar.
Thank you.
Great. We'll see you this evening, right? Okay.
Yeah.
Thank you. For you, this will be the morning.
So that will be morning for you, I believe.
Yeah. Mine will be morning, 8 o'clock tomorrow. Yeah.
Yeah.
Great. So
Oh.
what's the student name? The student who is helping there, what's his name?
Nipun
Is that
and Nipun Sharma.
Nipun Sharma? Okay.
Yeah.
And
Ahmed
And Amit.
is allowed? Ahmed, okay. Great.
So if you need any
Thank you.
help, just shoot an email to them or to me, so that will be shot out.
Yeah. Great. So tomorrow I will join earlier. So today
Yeah.
because the kids are watching the Super Bowl, I was
Okay.
kind of very noisy. I joined late. Yeah.
Okay. So it's not a problem. Thank you very much, Professor Chow, and thanks all the participants. Thank you, Mahesh, Amit, and Nipun. Thank you.
sir.
Great.
Thank you. Yeah,
Thank you.
good night.
Bye bye.
See you.
Yeah, dear participants, we have announcement that we have second lecture from 6:30 p.m. onwards today, and we have two tutorials after this second lecture, so you are requested to kindly join the sessions on time and be the benefited with the lectures of Professor Chow.